Similar triangles. In this lesson, we're going to talk about the properties of similar triangles. So there's two definitions that you need to know. One is congruent, and congruent is the same as equal. So that means that it's exact same shape. And then the other one is similar. And similar means that it's the same shape, but it's either scaled up or down. So it's going to look the same, except it's going to be smaller or it's going to be larger. So in example number 1, we have triangle A, B, and C. And this is similar to triangle P, Q, and R. So this is one of the properties of similar triangles. So the first property is that if we have these two triangles that are similar, well then the angles, the corresponding angles are going to be exactly the same. So we talked about the naming conventions of angles, and so I want to talk about now how else we can describe this. So angle ABC is equal to angle PQR, or that's saying that angle B, because it's always the middle one, is equal to angle Q. So angle B is equal to angle Q. And so we know that that's the case in this diagram because they both are denoted with a check mark. And then the next one is angle BAC is equal to angle QPR. So angle A is equal to angle P. So that's these ones right here. So angle A is equal to angle P. And you can see how just using this single letter convention is a lot easier to understand and to figure out rather than using all three letters. And the next one, angle ACB is equal to angle PRQ. Again, we're looking at those two middle ones. So angle C is equal to angle R. And again, we know that's the case because they both have a circle in that triangle. So if the triangles are similar, so that means they're the same shapes except one is either smaller or larger than the other, then the angles in the same spot or the same corners are going to be exactly the same. Another property of similar triangles is that the sides are going to be in proportion to each other. And again, we talked about the naming conventions about the triangle. So instead of calling it AB, which is the side, the vertices that make up that side, we can also call it angle or side C. So always across from the angle is the little letter across from that. And then angle PQ would be the same as, or side PQ, sorry, would be the same as side R. BC, which is the line segment that joins angle or B to angle C, we can also call that A because that's the side that's across from that angle. And we always label our sides as lowercase letters. So QR would be the same as P. So when we're talking about rewriting these fractions, instead of writing AB over PQ, I could write C over R is equal to A over P. And the last one, AC is the same as side B, and PR is the same as side Q. So again, you can either use it as the corners that make up that line, or you can denote it using this single letter to represent the side. Remember, angles are capital letters, sides are lowercase letters. So that's important to note as well. So now that we know that that's the case when we have similar triangles, we need to think about how we can use those information. And initially, when we're talking about well, what does that mean in terms of the sides being in a ratio of each other, or the ratios are going to be equal to each other, or the sides are going to be in proportion to each other, is another way that we can express that. Well, we're going to do that by using our example here. So there are 3 ways that we can prove that a triangle is similar to another triangle. And the first is by showing that all 3 angles are the same. So I'm just going to say 2 triangles are similar if, and we talked about this in that first property, all 3 angles are the same. And we call that AAA. Or all 3 sides are in proportion. And we call that side, side, side. And the last one would be 2 sides are in proportion. And the angle in between is the same. And we call that one side angle side. So when you're being asked to prove that triangles are similar, we want to think about writing a almost like a 5-sentence paragraph, where we have our introduction, our 3 proofs, our 3 examples, and then our concluding sentence. So for this one, I'm going to introduce my triangles. So for triangle ABC and triangle RST. So I want to show that either all 3 angles are the same. And I know what the angles are in the first triangle, but I don't know what the angles are in the second triangle. So that one's not going to work for me. Then I think about, are all 3 sides in proportion? So do I know the measurement of all 3 sides of both of my triangles? And I do. So that's the method I'm going to try to prove. So side, side, side. So I know that I'm labeling my triangle that the 8 is going to be side A, 10.4 is going to be side B, and 7.2 is going to be side C. R is 4, S is 5.2, and T is 3.6. And I know that in proportion, if they are similar, then side A is going to be in proportion to side R, which is going to be the same ratio as side B over S, which is going to be the same ratio as side C over R. So let's show that that's the case. Sorry, that's T, not R. So side A is 8, and side R is 4, and 8 divided by 4 is 2. Side B over S. So B is 10.4, S is 5.2, and if I divide those two, 10.4 divided by 5.2 is also 2. And C over T is 7.2 divided by 3.6. Again, I'm just going to take my calculator and divide those 2 numbers, and I also get 2. So we notice that the proportions are equal, or sometimes these are called the ratios are equal. Right? So we know that triangle ABC is twice as large as triangles RTS. So this 2 right here is our scale factor. And the scale factor just tells us how much larger or smaller one triangle is compared to the other one. So because all of our ratios are equal, then those are our three examples. Okay, so I can say that A over R is equal to B over S, which is equal to C over T, which we showed was 2. So therefore, triangle ABC is similar to, this is what this symbol means, that is that little tilde, that's what we call this symbol, is similar to triangle RST, and we know that this is the case by side, side, side. So we show that all three sides were in proportion to each other. So because these triangles are similar, now we can determine what the measurements are for angle R, angle S, and angle T. So I know that angle R has to be the same as angle A, and angle A is 50 degrees because angle R and A are in the same spot. I know that angle T has to be the same as angle C, and C is 45 degrees. And lastly, angle S has to be the same as angle B, and angle B is 85 degrees. So those are the three measurements or degrees for those angles. So not only have I proved that these triangles are similar by using my proof, side, 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 but I also now can determine what the measurements are for each of those missing angles in my smaller triangle. Let's do a couple more examples. So here in this example, I have triangle DEF and triangle JKL. So it already says that these are similar, so I don't have to prove anything for this one. But I want to know what the measurement of side F is and the measurement of side J, because those are my unknown variables. And because these are proportioned, our triangles are similar, therefore my sides must be in proportion. So I know that side D has to be in proportion to J, and E has to be in proportion to K, and F has to be in proportion to L, and all of these have to be exactly the same. And I know that because it already tells me that my triangles are similar. So what do I know about my measurements? Well, I know that D is 4. I don't know what J is. I know that E is 9. I know that K is 16.2. I don't know what F is, but I do know what L is. That's 11. So I've just written my proportions first, and then I've just substituted what I know from my diagrams. And now I'm going to do a two-part problem for this. I'm first going to solve for J, and then I'm going to solve for F. So let's start by solving for J, because that's the first one in my proportion. So I'm going to use my ratio or my fraction that has J, and I'm going to use the one that I know both numbers for. And I'm just going to use those two. I'm not going to use all three. I'm just going to use those two. And then I'm going to do something which some teachers frown upon, but is actually a really quick and efficient method to solve for proportions, is I'm going to do a cross multiplication. So I'm going to take my J and times it by my 9, and I'm going to take my 4 and I'm going to times it by my 16.2. Four times 16.2 is 64.8. And now I need to isolate for J, and I do that by dividing both sides by 9. And when I round it to one decimal place, I get 7.2, and my units are centimeters. So the measurement of J is 7.2 centimeters. And now I'm going to do the same thing, except I'm going to use the last two fractions, and solve for f. So my fractions are 9 over 16.2 is equal to f over 11. And I'm going to do my cross multiplication. So I'm going to multiply 16.2 times f, and I'm going to multiply 9 by 11. So 16.2f is the same as 99. And then I'm going to divide both sides by 16.2 to get f by itself. 16.2 divided by 16.2 is 1. So I'm left with 1f, or just f. And then I use my calculator. 99 divided by 16.2 is 6.1 rounded to 1 decimal place. So now I have the measurement for side f, which was my other unknown. So I used what I knew about similar triangles to set up my proportions. I substituted in what I knew from my diagram, and then I used only 2 fractions at a time to solve for the unknowns using cross multiplication and then my algebra skills to isolate for that variable. Let's do one more example. In this example, I have 2 triangles. I want to show that these triangles are similar. And so sometimes it's difficult to see what the triangles are, especially when they're embedded into each other. So we have one triangle, which is this small one right here, up here at the top. But we also have this larger triangle, which is right here. So those are the 2 triangles that I'm working with, the smaller triangle and then the larger triangle. So that's important to note when you have questions where the triangles are embedded into each other. So I want to show that these triangles are similar to each other. And so I'm going to start by introducing my triangles. So for triangle XVW and triangle XYZ, I put a little dash through my Z so it doesn't confuse it with the 2. But you don't have to. So I know XVW and XYZ. So they're in the same order, in the same direction. Well, what do I know? Well, I know that this angle up here in the top has to be exactly the same for both triangles because it's exactly the same, right? So I know that angle X is equal to angle X because it's the same angle. So both of those triangles share that top angle. I also know that angle V is equal to angle Y because that's given, right? It shows a smiley face in both of those spots, so both of those angles are exactly the same. And I also know that angle W is equal to angle Z, again, because it's given to me, right? They both have a check mark symbol, so both of these angles are exactly the same. So therefore, I can say that triangle XVW is similar to triangle XYZ because of angle, angle, angle. So all 3 of these angles are exactly the same. And because these triangles are similar, then we can use proportions to solve for this missing unknown, which is n. So let's start by labeling our sides now. So we know that across from our angle X is this angle, or side X, and across from this angle X is this side here, which is also X. So sometimes it can be confusing if they're both called the same thing, which is sometimes why you'll know that they label it using the line segments instead of the actual little letters. But either or is fine. I also know that across from angle W is 7, so that's this measurement right here. And I know that across from angle Z is this entire side right there. And so I can use that information, first of all, to find out what the height of this entire side of my triangle is, and then I can use that information to solve for n. So let's just start by setting up one proportion. So I know that X over X will be the same as W over Z. So let's plug in what I know. So 4 over 9, so small over the big one, is equal to 7 over this mystery number z, which I don't know what it is yet. So now I'm going to do my cross multiplication. So 4 times z is equal to 9 times 7. 9 times 7 is 63. Now I divide both sides by 4, so you can show it here if you want to, and then show that those cross out. So z is equal to 15.8 if I round up to 1 decimal place. And my unit is centimeters. I always need to think about what my measurements are. So next, I need to use that information to solve for n. Well, I know that this entire length is z. And if I subtract this little part, which is w, that'll give me the value for n. So n is equal to this z, which I just found out, which is 15.8, subtract 7. 15.8 take away 7 is 8.8, and my units are centimeters. If you have any questions about this lesson, please reach out to me. Send me an email, sign up for a virtual help session, and I'll see you in the next lesson.